And this is actually something that the RASC has laid out in its official documentation. So primarily, these are the things that the RASC is trying to do. One of those is to stimulate interest and promote and increase knowledge in astronomy and related sciences. In our current world, that I won't talk about too much, I think that's really important. I think that as a group of folks who care deeply about science and factual evidence, that it's important to try and do what we can to instill that love and passion for those things in the rest of the general public. And the RASC is a vessel through which we can try to do more of that. We're also here to acquire and maintain equipment. Libraries and other property necessary for the pursuit of its aims. So, this goes across a lot of things, but the RASC actually has a wealth of documentation resources that I'll get into in a little bit. Locally, we have our Glenley Observatory, for instance. We have a collection of lunar scope telescopes that we can talk about. So there's a lot of things that we try to do as a group to pull things together, right? We want to. It's more efficient to do things as a group in those ways than it is, to do them on your own unless you're rich, right? Like I'm not going to go build my own observatory, right? But I can take advantage of the one that the club has because we've all pooled our money together, right? So it's like that, I guess. Also, we then take all that knowledge that we have and we publish journals, books, and other material containing information on the progress of astronomy and the work of the society. So I feel like this does a couple things. One, it's there to educate, but it's also there to celebrate and recognize the amount of work that the amateur astronomers in this club do. If you do read the journal, and I'll talk about them a little bit, there's just some amazing stuff that people are actually out there doing, and they're mostly just amateurs. When I say amateurs, I mean people that aren't making money at it, but there's a lot of hard work that goes into it. The RASC and more administrative sides of things, we receive and administer gifts, donations, and bequests from members of the society and others. Good to use money. And we also make contributions and render assistance to individuals and institutions engaged in the study and advancement of astronomy. This extends to, at science fairs, we will put up awards. In return for this room, we actually give a bursary to St. John's College every year, for instance, right? So trying to do those things. We also, we'll be giving away solar filters for the eclipse and that sort of stuff, right? So there's a lot of stuff that the RASC will give away in that capacity. So let's get into the history, because we've got a lot of history. So the RASC originally started in Toronto, surprise, as a Toronto Astronomy Club, eventually got bigger and incorporated itself. So 1890 is the year that we've kind of picked. There's a little bit of fuzziness there too, but who cares? 1890 was also the year the vocations started being produced. And then in 1903, it was officially renamed to the Royal Astronomical Society of Canada. So royal designation is kind of funny. Like, I think it's like, I remember when I first heard about the RASC, and I was like, so when I heard about the RASC, I was like, that's kind of like a hoity-toity, thing. Why would I want to be? I guess I want to be a member of that. Like, there are a bunch of nerds like me, but what's this royal thing all about, right? And it actually came about when George V visited Canada, which I'm sure you'll remember, right? No, he was visiting Canada, and at the time, everyone under the sun, every single club was putting royal in front of their designation because a royal designation in front of their club name because they could get it, right? So they were actually, you would just go to George V while he was coming through your town and say, hey, can I, well, not obviously personally with him, but you would submit to get the royal designation, and you got it. So that's how we got the royal designation. Thanks, George. Whatever, right? So now we have this, but at least we got a cool acronym out of it. We can say RASC, right? You know, so you get rascals, it works, right? And then from 1904 to 2007, nothing of significance happened. Absolutely nothing. Okay? But in 2007, I joined. So now I'm going to be selfish, and I'm going to talk about myself. So I think that everyone here has their own story about how they got into astronomy, how they got into the RASC. I think those stories are cool. And you know, if we're hanging around chatting, you know, at the refreshment break or Boston Pizza, I'd actually be really curious to know how you got into this. I don't think I asked that enough. And Mike Caracas, who's our newsletter editor, might be starting up a thing similar to this. So I'm not going to try and move in on his space, but I think it's cool just to hear these stories and how people got into it. So for myself, I initially got into astronomy as a result of when I was 12 years old, and my dad took me out to see Comet Hyakutake. Okay. How many people in this room remember Comet Hyakutake? Pretty good. How many people remember Hale-Bopp? Yeah. So I thought Hale-Bopp kind of sucked in comparison to Hyakutake. As a kid, like, it just wasn't as impressive, you know, to me. So like, that comet has always held a special place in my heart because it was really the thing that kind of blew my mind, you know, and really got me into it. So. You know, I also had the classic Saturn viewing experience where I was pretty convinced that, you know, the guy had taken like a little sticker and stuck it on the end of the telescope, you know, to try and fool me into thinking that this was, you know, a planet that I was really looking at. If you've never seen Saturn through a telescope, please do. Like, I'm not going to. But anyway, so, you know, after this, I thought to myself, okay, well, I really love astronomy. So I went off and I started studying astrophysics at York University. Now, here's the funny thing. I have a degree in computer science now. So I won't tell you what happened there, but let's just say that math is hard. So, but when I was at the university, I was actually working in this observatory. And when my supervisor heard that I switched to computer science, he was like, hey, you know how to write computer software. And he got me to write automation software for the research process. I was like, God, this is great. I love it. Right? I got to kind of marry my two passions. It was a lot of fun. And then when I was leaving university, I was talking to my supervisor, and I was saying, you know, I'm really going to miss this. You know, I was part of an astronomy club at the university, and we did all these observing nights, and I got to talk to people about this stuff, and they listened to me, and I don't know why. But they listened to me. It was great. I loved it. Just like you guys. So I was really sad to leave that. He said, "Oh, have you thought about joining the RASC?" I was like, "The what?" You know, I never heard of it. And then I realized that I'd actually been reading the handbook for years at this point and had no idea that was, you know, that was the club, right? So yeah, so I joined the RASC, and I don't know, I haven't looked back. So it's been pretty great. So the RASC has quite a number of resources associated with it. We have publications, which I'll get into. Actually, I'll get into all these in a little more detail. We have publications, we've got the website, certificate programs, discussion groups, and email lists. Okay? For publications, there's the journal, the handbook, there's a beginner's observing guide, and then there's also a bulletin that goes out via email every month. So that's a lot of words. But the Journal of the RASC, I think is a fantastic publication. Our former now Center President Jay Anderson was the editor of this, and he's handed it off now, but they're still running with it in fantastic fashion. There's a lot of really, really interesting articles in here, and like I was saying earlier, a lot of time and effort goes into a lot of those articles. I'm not going to say that everything you're going to pull up the journal and not everything is going to interest you, but there are some really fascinating articles in there. And yeah, it's cool because it's mostly RASC members or just other contributors that from the academic side of things that are feeding into this. So it's a worthwhile read. I recommend checking it out. You can get a free off the website, although I do know that the download numbers are really low. So if you get the printed copy, there's a chance you might actually read it. Just throwing that out there. The handbook. So I think the handbook is a thing that people look at as this tome, of like, I'm never going to get through all this maybe. And it's not meant to be that. It's a really handy, it's a handbook. It's a really handy collection of astronomical information, right? And as much as I love my smartphone, right, and all the technology that's around us, when I'm out in the middle of the night, under the stars, and I've got a red flashlight with me so I don't ruin my night vision, right? The last thing I want to do is turn on my phone and go Googling something, right? Well, guess what? Everything that you possibly need to know is in there. There's an incredible amount of information in there. So I do recommend bringing it out with you. It will come in handy, and just try to remember that you have it, because you get it free with with your membership. So I recommend the Sky by Month section as being particularly useful, because if you haven't been out for a while, it can really help to pull open the Sky by Month. If you happen to be out, and it'll give you an idea of what's out there, right? What is in the night sky right now? What are some good things to go looking for at that time? And if you didn't believe me when I said that it's a freaking tomb of knowledge, this is just like half of what's in there. Everything you could really want to know in a fairly concise, dense form, right? I mean, this. Right? Oh, yeah, by the way, sorry, when I said half, I meant a quarter. Because there's this, right? There's an incredible amount of information in here. And it's not a thing that you're going to, you could sit back and read it there are actually some really well-written pieces in there, and I do recommend checking those out. But just using it as a reference guide is pretty fantastic. So, Sky News. So, I'm not going to lie, I actually just kind of I Googled most of this presentation. So, according to Wikipedia, Sky News is a 24-hour British and international satellite television news service with an emphasis on UK international news stories. Not right? No? Well, there we go. Okay. So, Sky News, not Sky News, is a magazine that the RAC now owns. It's published 6 times a year. You get it free with your membership. And it's good. Astronomy magazine. Good articles. It has star charts that are relevant for for when it comes out. It'll have it's got letters to the editor and all that good stuff. So it's pretty good. It's another good resource, and again, just something worth keeping an eye on as it drops into your mailbox where you're not used to getting mail, because it gets mail anymore. So we go to the Winnipeg Center. So as I was saying, there are many centers across Canada. We are one of them. I don't know how big or small we are in comparison to the other centers, but we're up there. We have about 200 members right now. We've been around since 1911, so we've definitely been. We were definitely one of the earlier centers. And yeah, we have monthly meetings, which is what this is right now. So, and these meetings are, if you weren't aware, if you thought that you had snuck in, you didn't. These meetings are free and open to the public, so welcome if you're new. We have a website, which I keep up to. We do want to do more of the website. I keep it up to date with the upcoming meetings. So if you want to know what the topics are going to be for the next meeting, it is up there. So each meeting will tend to pop up following this one. So like after tonight, there'll be another meeting that'll pop up there. So, but it has information like on our upcoming store party and that sort of thing. There's also a contact form there too. We actually get a lot of traffic through the contact form on there. So if you, I respond to a lot of the emails, but there's also stuff in there about the telescope loans and the observatory. So if you ever want to get in touch with us and you have no idea how, if you use the website and go to the contact form, I promise you at some point I will respond within reason. So I'm trying to be as legal about that as I can, right? But no, I do respond to every email that's come through. So unless you're crazy, don't be crazy. Nobody crazy. Well, there was one that whatever. I won't get into that. Sorry. It's okay. It was just Jerry. It's fine. So we've also got an email list. The email list is it's administered by the U of M, and it's kind of an older way of keeping in touch with people, I think, but it functions well. And it's basically just if you're subscribed to this email list, you will get an email whenever somebody posts something to that email list, right? This is very handy for when, say, there's a meteor shower, coming up, and you haven't really talked to anyone, and you want to know if anyone's going out. Or any random moment is clear. People say, hey, we're going to go observing tonight. Do you want to come? Right? So the email list is good to have. We actually don't have a discussion forum anymore. This is an older slide. My bad. But yeah, the Winnipeg Center also has loaner scopes, which I'll bring up again later. And we've also got our Glenley Observatory. I'll talk about the loaner scopes and Glenley Observatory now. So the loaner scope program right now is administered by Stan Runge, who's sitting over there. And he is, you Stan. Yeah, no, you. But he's done a fantastic job recently, just in actually it's been a couple of years now, of really kind of coalescing all of our telescopes together that we have. So I don't know what the list of telescopes we have are, but we've got a couple of 8 inches, and I think there's a 6-inch, and we're also putting the PST, which is the Personal Solar Telescope, into rotation. So this is a small telescope, but it has an H-alpha filter on it, and you can use it to look at the sun safely, which I think is really cool. I've never personally owned a PST because I don't know, spending money that I can only use to look at one object is I just haven't hit that point in my astronomical spending yet, I guess. So, but it's cool. It has one, so if you ever want to use it, you can. The loaner scope rotation goes on a month-by-month basis, but yeah, we're also getting a mount for that telescope as well, so you won't have to track along as the Earth rotates. The Glenley Observatory, which I'd like to think of as hopefully in the future the first underwater observatory, fully functional. I haven't actually checked the flood forecast lately, but maybe that joke won't actually have to be a thing. But yeah, the Glenley Observatory is it's a short drive south of the city. So you get out of a little bit of the city lights. It's not perfect dark, but we've got a warm room. We have a telescope with a 14-inch, and we've also got a 12-inch dog, I think. And there's a pad as well for if you just want to bring out your own scope and set up there. And I know quite a few people in the club do go out there and take advantage of that. So I do recommend it, heading out there. We also do members observing nights. So Brian Stack is the guy. He's our observatory director, and he'll be talking later tonight. And he does run these member observing nights, and they're a chance for you to get out, get familiar with the observatory. Recommend that. Winnicentrics. This isn't correct anymore. This is our newsletter. So this is something that we send out. We used to send out every 2 months, but Mike Caracas is crazy and has been sending them out every month and doing an amazing job with it, which is really cool. I'm very happy with this. But yeah, we've got contact information for council members in there, upcoming meeting information, center news, astronomy news, recap of recent events. Now he has articles in there. So Kevin Gallagher has been writing some stuff, and there's been other people who have been submitting things. So yeah, so it's just kind of it's more local. It's more like a local newsletter. You will get it if your email address is in the national list. So if it's not, you need to get that corrected. Jay mentioned this, I think, in an email to the email list. But yeah, so your national email needs to be correct. So if you're not getting the Winnipeg-centric newsletter, if you're not getting Wincentrics, you need to go to the national website and get your email changed. You can contact them. Shouldn't be a problem. So, we've talked about all the stuff that, the RASC has to offer, and that kind of thing. So, maybe we'll just pretend that wasn't a sales pitch. And we'll say, you want to get involved, right? Like you want to. And when I say involved, I mean like what are you into, right? When it comes to astronomy, astronomy is a big thing, right? Like, and I think when I say astronomy, I'm also talking about, the RASC quote-unquote brand of astronomy, right? Where we're trying to educate people, right? So you can get into things like light pollution abatement. I shouldn't have said light pollution. But light pollution abatement would have made this really long. Like, I'm not saying you should promote light pollution. I think that's kind of obvious. I had to trim this down. But public outreach, space exploration. I mean, we have tonight's featured presentation is about the New Horizons project, which is amazing. You can get into stuff like cosmology, history. I love astronomy history. I think it's fascinating. It's just a that I didn't even have, up until years ago, as I just started reading those books, but yeah, stuff like that too. Sketching. We've had people who have gotten into sketching recently who have done just amazing things, and it's something I don't think you see enough of. And I find that like sketching, for instance, is as cool as astrophotography is, and the subject field, like I love sketches because they show there's this personal side to it, but there's also this kind of quality of it that I think better reflects, what your eye sees and what you focus on, and what is, what's special about what you're looking at, right? So sketching is a thing. Imaging, again, astrophotography, cool. You don't even have to spend a lot of money to do it either, right? There are very, very economical ways of getting into astrophotography. I'd also throw out light pollution abatement as a thing that we have made, thanks to the work of some people. I'll just throw it out there. Tim Kennedy, Sandy Shuchuk, and I know Dennis has been very, very much involved in this as well. We're getting close with Spruce Woods, which I think is fantastic. It's been a long ride, but we're pretty close there, and I think we will hopefully have it as a dark sky preserve in the coming year-ish. So that'll be pretty amazing. So anyway, so if you like I said, there are people doing these things. So if this is something that interests you, reach out to the club. When we get into if we want to talk about observing now, right? If you're really into observing, you can find people who specialize in each area of this, right? If you want to get into your deep fuzzies, if you want to do solar observations, you can borrow our PST. If you have a C8, you can do planetary observations. Lunar observations are very easy as well. Occultations are a thing that you can do. These are opportunities for you to get out there with your telescopes and look at the night sky. So, how do you get involved? This is okay. Well, I said the sales pitch was done. That was mine. Monthly meetings. These beginners, I don't know what I'm doing out here, right? I've been doing these beginner sessions for 7 years now. I don't know what I'm doing. I'm just standing out in front of you talking right now. This is, I do this every few months. I pick a topic that I think is interesting that I can try and help inform you about, and I do it. And it's just something that I offered to do, and I've hopefully not done a terrible job. But I think that if you want to come up here and talk about things, if there's something that you're really passionate about, talk to us. Come up with come up to us with something that you want to tell us about. And we can try to fit that into the meetings. Heck, if you want to take over these beginner sessions, that'd be cool too, right? beginner sessions. Maybe, you know, if you wanted to lead me a little bit of this, that'd be pretty cool. You know, but of course, you don't have to do public speaking. But if you want, like we have other public events. You know, there's a Fort White dinner and show that happens every year that Marnie just kind of threw, you know, like, well, not threw together, she put a ton of work into it, but, you know, she brought us into it though, right? You know, and this is just a night where we go to Fort White, we have a dinner, and we talk about astronomy, and then we try to do some observing if it's clear, right? And there's a bunch of other things that go on like this. We've got Astronomy Day, there's other public observing events, and I find I get a lot of satisfaction out of showing people things through a telescope. Because in many cases, that's the first time they ever done it, right? That is a very common thing, right? And some of the reactions that you get are pretty amazing. You can also get involved with council. We have 5 councilors, a vice president, a secretary, a treasurer, we have a president, we have national representatives who interface with the national. You know, so there's lots of room to get involved. And the council is basically like, I don't know, we're people that meet up every few months, if I don't forget to schedule a meeting. You know, we sit around, we drink beer, we try to make decisions. That's about it. Members observing night, like I was saying before, you can get involved with that, help out, or just come by. Science fairs, the Manitoba School Symposium, Science School Symposium is coming up, and we're actually going to be giving an award out, right? So, I mean, if you want to go off, if you want to talk to some kids about science stuff, come talk to me, and we'll actually get you out there being a judge, right? It's a really easy judge thing to do as well. You actually need to spend lots of time like hearing cool, fascinating things from school kids. It's fun. Educational programs. I have done talks at some high schools and stuff like that. So, you know, there's ways of getting out there. And of course, the Sprucewood Star Party. Like this has always been a highlight for me. This is a chance for us to get together with a bunch of astronomers. So what we do is we go to the Spruce Woods, we plop down our tents, and we set up our telescopes. There's a friend once told me she saw it as Folk Fest for nerds. So, which I think is funny because I think Folk Fest is for nerds, but whatever. But you get the point, right? You know, I think like this is one thing that Jared has always gotten at is that like, you know, at Spruce Woods, if we have 3 nights, you really need one of them to be cloudy, because staying up all night, what's going to happen is, you know, the next day you're going to be up all day hanging out with people, right? Because it's a great group of people to be around, so you don't get any sleep, right? The other problem too is that like on a cloudy night, it's kind of nice to actually go mingle a little bit, right? You want to go spend some time with people, right? So highly recommend if you're a member, come out to Spruce Woods, totally worth it. You know, even this joke is so old now. Even if you forget your 10 poles. So I don't know how many people in here remember this. So my first star party that I went to, I had been camping the weekend before, and I had totally forgotten to pack up my 10 poles. So I packed up my tent and threw it all in my car, right? Drove up there, and then I get there and realized, oh no, I totally forgot my 10 poles. I had no way of keeping my tent up. So, you know, I mentioned this to a couple people. Remember, I'd only been part of the club for, I think, barely a year at that point. I don't know how well I really even knew people at that point. And I think I think it was Tim Kennedy's RV. And they found me a couple of those old, like, really old style, you know, from the older tents, those big poles, right, that you screw into each other, right? And ended up using a bunch of those to prop up my tent like a TV. And I slept in that whole weekend, and it was great. So, you know, if you're, I mean, I'm not saying that people are going to provide like everything for you, but you know, you'll find a way. Pretty close. Pretty close. Pretty close. So, anyway. Just to finish off, I want to talk a little bit about, you know, something of a perception of mine where I think the RASC can get this kind of impression that, like, it can come off as a bit of an old boys club. It's one of those hobbyist clubs that, you know, tends to cater to old guys. Sorry, old guys. Oh, sorry. I'm sorry. I just gotta say it. Right? So it does. I know. This is it's like I just got elected, so I'm safe. I'm totally safe. Right. We don't have any impeachment. No impeachment in the bylaws, right? No. Okay. So, but in all seriousness, I will say that it gives that impression, but it isn't one of those places, right? I came into this club as some dumb kid, and I was very much invited, and I've seen women who have come into this club and have been, given as much support as as they could ever need, and encouragement into what they want to do and where their focus is. So, yeah. So I don't want anyone to get that impression, but just to drive it home, when you come to these meetings, you don't need knowledge, right? You need curiosity, right? Knowing things is not the point. Learning things, right? You don't need gadgets, right? You don't got a lot of money. I was a poor student for a long time. Now I'm a poor homeowner. I don't have to, I can't, I don't put a lot of money into my hobby, but I still get a lot out of it, right? So you don't need gadgets. You just need clear skies. Good luck. So you can get away on a budget, totally fine. And just try to remember that the stars belong to everyone. Thank you. Although I'm 33 years old and I can't use a touch pad. Oh, hello. Didn't see you there. So that was my smooth transition. Hello and welcome to the March 2017 meeting of the RASC. This is what happens when you are the president and you do the beginner session. I'm saying it's March 2017, but we all know this is an alternative fact. It's not actually March, because there's no way with that cold out there that it is. I'm still running the truck, folks. So, so welcome. Do we have any new members out tonight? Or even non-members? New people, put your hands up. Cool. Okay, welcome. Refreshment break or anything like that, come talk to me. But also, do we have any members of the council here tonight? Okay. New people, meet council members. Council members, meet new people. Try to, make that happen. But yeah, no, seriously, if you're new, come by all, even if you're not a member, whatever, come talk to me. I'm really interested in chatting, obviously. So on the agenda tonight, we'll run through some announcements. We'll go through what's up with Brian, and we'll also go through what's new with Ian. And we'll have our refreshment break, probably around 8:20, 8:30 or so. And then at 9 o'clock, we have a pretty cool presentation. We have Dr. William B. McKinnon talking about Pluto, entitled Pluto Revealed, Results from NASA's New Horizon mission. And we'll talk about that a little bit more, but I'm actually kind of excited. So, more maybe. I'm kidding. So, but let's get into the boring stuff. Boring but important. Club business. The April meeting, so we meet on the second Friday of every month. Next month that actually lands on Good Friday, so we've moved the April meeting from the 14th to the 7th, just because of Good Friday. So if you show up here on Good Friday, there won't be anybody here. Chances are the university doors will actually, the doors to this college need to be locked, so change calendars. That'll be updated in the on the website, and also shoot out an email to the membership about that as well. So we actually, we just had a council meeting, and it turns out that our finances are in pretty good shape. We try to keep some money around should we need to do something about Glenley and the flood situation. It is in the floodplain, and it has flooded before, so it's good to have a reserve fund in there just in case. But we do have the ability to to spend some money and really just give back to the membership. So a couple of the recent items that we've done just as of this week, we're going to be purchasing a tracking mount for the PST, which is sitting right there, like I was saying earlier. So that'll allow the tracking of the telescope to be nice. And we're also getting some video equipment for Abdul, who's been thoughtlessly recording and broadcasting our meetings to the internet. So we thought that would be a really worthwhile investment, just because the quality hasn't really been up to what we might want. And so hopefully that'll help. So my pitch to you is, if you have some ideas, a few little projects maybe, or something that you think would help us as a group, by all means, reach out to myself, reach out to a council member, and we can certainly look into it. Volunteer opportunities coming up. We have Astronomy Day on Saturday, April 29th. I organized this for the past several years. We usually go to chapters, and then we try to get out at night and do an observing event somewhere. The chapter side of it always goes well. We always get a decent crowd out. Chapters is very accommodating. There are people who read books, so they tend to have a little bit more interest in astronomy. They at least seem to be more receptive. It's a fun day. I recommend it, but I am looking for a volunteer to organize. It'd be nice to have somebody else take that over, and we'll also need some other volunteers. I'm going to be there anyway, but just to have somebody kind of to work out the chapter stuff and work out an evening observing event. So if you are interested, reach out to me. I'll also shoot this out to the email list as well. Excuse me. Also coming up on Saturday, May 13th, we have the Science Rendezvous, which is a thing that happens across Canada on this date. But the U of M is kind of setting it all up. They're the ones organizing it. So this is really easy. The U of M basically takes care of everything, and we just show up with some solar telescopes during the day and help out. Right? You don't even need a telescope. Just come by and try to help. Right? So they do, and there's also food. So they're for the volunteers. So anyway, if you're interested, talk to Jay. You will, or just talk to me too. And I'll put you down. Hammock Marsh Astronomy Night. These are still happening. Jerry was telling me that the most recent one, they had about 60 people out, which is pretty cool. And they're continuing to do these. The next one is Wednesday, March 16th from 7 to 9 p.m. They do an indoor presentation in the theater, and then they go outside to do some observing areas clear. There is a $10 entry fee. It's $5 if you're a member of Hammock Marsh, and then that is actually waived for RASC members that are there to help out with their telescopes. So if you come by with a telescope, you get it for free.
Brandon, it's on Thursday.
Is it Thursday?
Yeah. I know, because I got a deadline on Thursday.
I'm sorry. Okay. So Thursday. Did I get the day wrong or the date wrong, or both?
Date's correct. Day is not.
Okay, that's fine. Okay, I get it. Yeah. Okay. So yeah, Thursday, March 16th. Thank you. Appreciate it. Probably because I was looking at the open house slide. The open house is something that happens at the U of M. And these happen on the last Wednesday of every month. And the next one, they typically start around sundown, and the next one's happening March 29th at 7:30. This is something that we try to help out the U of M with. I know Brian's gone for the past few, and I don't know if anybody else has, but it's a way to interface with them, and I know that they appreciate having us out there with, if we want to, if we have telescopes and it's clear, that definitely comes in handy. So, I've already talked about telescope loans on the beginner session, so I won't spend too much time on this, but we do have them. So if you're interested in, getting a telescope, for a month, they're in good shape, and they're pretty well constantly checked out. But you can talk to Stan. He's over there. and talk to him, and he'll hook you up, hopefully, with a telescope. Little pauses we're confident in doing that. I also appreciate the nervous. That's great. We also have Lonely Observatory, which is run by Brian, who's over there. Talk to him because he can get you a warm room key if you give him a deposit of how much? $10? Okay. Wasn't it? Didn't it used to be $5? Yeah, so it's a $10 deposit. You can get a warm room key, which means that you'll have access to it. If you want to use the observatory, you'll have to go through a little bit of training, but it's there for you. It's something you can take advantage of. Yeah, and we do. Do you have a members observing night planned? Do you have a thought on when you're going to do the next one?
I was thinking about next weekend.
Okay. Okay. So next weekend, next Saturday night, if it's clear, you can check in with Brian, but we may try to do one. Yeah, it's a little chilly. Also, the moon is out. Okay. So let's jump to what's up with Brian. Unless anyone has any other news, any other announcements or questions?
Yes. I brought along a few copies of the book that Fred Espenak and I wrote about the solar eclipse. I know some of you have ordered it, but I get them a little cheaper than the rest of you. But I don't get them for free, so they're $39.95, I think, on the RASC site. So if you want one from me, it'll cost you $25. Plus $5 for an autograph.
You can get Fred's autograph?
Matter of fact, I can, but it won't be till later.
All right, so this is what's up for March. Okay, so for the planets, not much is really happening. Mercury's going to be behind the sun. Venus is going to be stationary. Jupiter is going to be doing a retro motion for the next couple of months, I believe. And of course, Saturn is the morning planet. Now let's see it from Earth here. This is the old view I'm going to have for doing the planets. I'm going to try something different this time. Hopefully this works. This one. It's a little more animated. Is it going?
In real life.
It's running in real time.
There you go. Wind it up.
It is going, okay. I think it is going. All right, this is my new way of having to show the planets, okay. So we're outside the solar system as we are. Pluto is kind of a unique planet itself because we're not a planet anymore. But okay, we're going to zoom in a little bit more. So we got Neptune here, we got Uranus. Next we're going to zoom in a little bit more. Next we're going to have Saturn and Jupiter up here. Try something a little different here, this works. Now we're going to zoom in a little bit more for the inner planets. I really like this model a lot better because Mars is more elliptic. Gives a two orbits of the planet. Of course, as we mentioned before, Mercury is going to dip behind the sun a little bit. Venus and Jupiter is going to be in its stationary orbit or motion here. And of course, the orientation of this is a little bit more. This is the top view of it. So these stars here, you'll see. This is if you're in the southern hemisphere, you'll see these kind of stars. So it seems to be working right now. I think that's all I'm going to really say for now. I think eventually it's going to zoom out a little bit more. If my time is right. But yeah, there we go. Going to zoom up a little bit more. Good. There we go. Okay, I'm just going to move on here. Hopefully this works. Okay. Try something a little different. Okay, so like I said, Saturn is the morning planet. There's Saturn right here. We got Jupiter up here. This is what, roughly 4:30 in the morning. Next in the evening, we have Venus up here. We do have Mars up here. So 5 o'clock. And then after midnight, I kind of set it for like 12, a little after midnight, because Jupiter is going to be quite high here, and of course Saturn starts to rise around just after midnight. Next, for the celestial calendar. Okay, so of course, it's going to be daylight savings time, so we're going to have to advance our clocks 1 hour. Of course, I mentioned Venus will be stationary. We also have the zodiacal lights. It's going to happen the next couple of weeks, but of course, you're going to be competing with the moon. So hopefully next week you can see it, but it happens only evenings. Of course, Jupiter, Saturn's going to be just a couple of degrees south of the moon. And of course, we have the new moon on the 28th. Next, okay, a little bit about the zodiacal lights. Now, for the new members, you're probably not really familiar with it, of course. I kind of simplified this a little bit more. Okay, it's just a interplanetary dust, very pebble-sized to very small wavelength type dust particles. It's kind of a radiant pyramid light there. Of course, it's on an elliptic plane, and of course, if the geometry is right, you'll be able to see it. And of course, February, March is going to happen in the evening. In the fall time, will happen in the morning. All right, this is a little bit more about what's going on, how to see the zodiacal lights here. Okay. We have, of course, there's the moonlight or haze mixed light pollution, anything like that. It's going to kind of inhibit the observing part of it. Okay, let me show you some pictures of what it should look like. Well, this is a little view about, that's supposed to be Jupiter, that's supposed to be Saturn, so that's how big the dust clouds are on the edge. Okay, now this is back into Arizona. A couple of weeks I was with a bunch of friends there. Now this is a wide-angle shot of what it should look like. So you kind of see there's like kind of a small or like a soft pyramid glow there. You can see. Here's another one. I like this one because with the Sky Tracker I shot with, thanks to Kevin there. And of course it was tracking it. Now it's kind of big here. I'm going to show you another picture. By the way, that's Jay there. The guy's like a machine there. He's like disappeared at 7. It shows up at 4 o'clock in the morning. Like, you know what happened. That guy never sleeps, I swear. Anyways, okay, this is a much better picture, I think, for the zodiacal lights here. You kind of see, you know, it's dark here, so it's kind of a soft pyramid here. Next, okay, about comets. Let's try that. Now, 45P, because it's very diffuse comet, it's not really good. You can't really see. None of these comets you can really see visually, so I tried back in Arizona. It never worked out for me. All right. Okay, what else? Okay, so this comet was, Perihelion was back in December. Johnson's coming up. It's not bad, I guess. It's going to increase its magnitude by 1, but it's not going to be all that bright. But it's reached its maximum brightness around early June. Next, we have that 2P one. It's too close to the sun to really have a look at it, but we'll increase its magnitude. It's supposed to be around 4 or so, but we'll see. Now, 41P, this one, it's kind of hard to find, but we'll have a look at it in the apps. Oops, a little too far there. In the apps, they call it 41P TGK is what to look for if you want to try to look it up in your software there. Okay, next, you want to have a look at it. Okay, so what I tried down here to do is around 2 a.m. in the morning. And of course, that's the Hercules constellation there. We have the 45B Honda there for the Comet, and then we have the Johnson here. So it should be relatively easy to have a look at it, but it won't, nothing you can see visually, yeah. All right, now this is 2P here, as you can tell, it's pretty close to the sun, but it's supposed to be at a magnitude of roughly around 4. Who knows? We'll see, but it's pretty low in the sky, if you ask me. All right, here's my another attempt of animation here. This is Comet 2P. And let's see if that's working. It's not. It is. Okay, there it is. Hard to tell. All right. Okay, the purple there is the Comet 2P. It's in the counter rotation, counterclockwise. That's the orbit for it right there. You can tell it's going to come up to the sun, so it's perihelium is going to be the next little while, or mid-month or so. Okay, there's Earth there, you can see, but you have a really good idea of the orbit of some of these comets. Next, I don't think I have anything else. Okay, next, here's another example. This is try that. Is it working? Yeah, okay. So this is Comet Johnson here. Again, it's a counter rotation there. The purple represents the comet. That's the location of it right now. Of course, if you looked at the earlier slides, it's pretty high up. Earth is the blue star, or the blue dot right there. And we'll zoom in a little bit more. We'll pan around, kind of give you an example of where it's at, the comet. Remember, these other stars you see here in the southern hemisphere, and give you an idea of the orientation of it. And there's the comets moving a little bit further there. And it wasn't easy to do this. All right. I had to run it through 3 different softwares to get this working. All right. One last one we have. Okay, 41P. Let's have a look at that. Okay. Again, this is the purple. It represents the comet, and of course it's counterclockwise rotation. It's pretty close to Earth. Look at it. Pretty close. But it's only like a magnitude of 10, I believe I said 10.5. But that's just to give you an idea of the orbit that some of these comets have. And I think that's it.
What's up, Stan? Yeah, sorry, yes, Stan.
I was just going to make a comment on the comets. Some of us were down in Arizona last month, and we got to see them. And the interesting thing about the field is large. It's a very green type pack kind of a comet. So it was sort of interesting in that perspective that the color was very rich. Johnson was an interesting comet because it looked like you normally would expect a comet. A bright halo head to it and a long tail leading off of it. It's a fairly substantial tail. We're seeing it best because we're taking pictures of it. Honda was another one. It's coming in at an interesting angle because of the perspective that you look at it. It had a very broad tail, so it's a very elongated with a bright spot in the center. So the one thing about these 3 comets that's kind of neat is they all show you the comets to be like a very distinctive range that you can see them at. The Johnson and the and what we call Honda, and those 2 specific comets, they're quite high in the sky actually, around midnight. So they're fairly easy if you want to take pictures of them or try to. They're ones that you should try to go after. Just some comments. Questions?
So Ian will be telling us all about what's new in the academic side of astronomy.
Okay, what's new in March? In other words, news during the past month. There were lots, and of course, what you get is my take on what I think is particularly significant. And so the first thing, it's kind of appropriate to Brendan's comments a little bit later on, and that's the business of light pollution. It turns out that next year is, I think, the 30th anniversary for the International Dark Sky Association, and it's now being, those sorts of studies of dark skies is now an academic pursuit. Okay, so the world's first academic center dedicated to dark sky studies, okay, is recognized by the University of Utah, the College of Architecture and Planning. And 30 years is a long time. The interesting thing about the International Dark Sky Association was that it was founded by a professional astronomer and an amateur astronomer. And so more and more the importance of hitting dark skies is being recognized. So this particular consortium is composed of 25 university, industry, community, and governmental partners. And the research issue is, basically they're looking at the global issues of light pollution, public health, economic and environmental impacts of what's called the so-called disappearing dark. Interestingly enough, the Natural History Museum of Utah, they recently received an International Dark Sky Association Light Museum Award. So this is what you can do, actually preserve your dark skies. Amateur involvement in dark skies, of course, has been long-standing, and we see that. How many people here have actually used the Doral scale? How many people know what it is?
You know it's a number.
It's a number, okay. How many people know who Doral was? Oh, he was a comet hunter. A comet hunter. And in 2001, he published, actually, in Sky Telescope magazine, a scale by which you could basically visually inspect the sky and assign a number, basically a quality number, to the sky. And it's been quantified in a number of ways. A number of you may, in fact, have dark sky meters, so you measure basically magnitudes per square arc second. Natural sky level is that nice red line at the bottom. And of course, as things get worse, that red line just moves up farther and farther. Now, it's one thing to see the numbers. A much better way of looking at that is actually to see something that you can put together. And this is a video, actually, it's video number 2 of an award-winning time-lapse of basically photographs at various locations throughout the States at various levels of light pollution. So here you can see light pollution level 7, 7 on the Bortle scale. One of the things you may notice about this is the number of planes in the sky all the time. And if you actually can see the motion of stars across the sky, you get some indication of how long each of those little clips are. But you'll notice a dramatic difference as the light pollution levels drop. Needless to say, there was a lot of planning that went into producing this video. With a little bit of luck, you would have seen Orion in all of these pictures. So how many people have been in really dark skies? And you can check out his website. He has some really interesting time. Second item. It was an anniversary a little while ago. Also, funnily enough, a 30th anniversary for Supernova 1987A. And early on in the year, Hubble snapped another picture of the region there. So you actually see supernova remnant actually in the center of the frame. One of the things several of the things to notice about this is this isn't done with a color camera. All right. It's actually a composite. The red, of course, is characteristic of hydrogen gas, and so that's how you actually see it by eye. The stars the colors of the stars, however, okay, were actually added in after the fact. So it's one thing to sort of remember when you're looking at some of these pictures. This is probably a picture that you may have seen, okay. It turns out, of course, that the supernova event was observed very early on in the game. Turns out that it's probably one of our best studied supernova of all time. And that means then that what you need to do is you need to hold a symposium on the 30th year. And so you choose a good location. Okay, we talk about supernova and cosmic rays, and you devote a session to supernova 1987. Of course, what's been in the news lately is Goldilocks and the Seven Dwarfs. Or did I screw that up a little bit? Well, I couldn't help putting in the Seven Dwarfs there, just simply because we've got regular planets in this particular system. The system name is TRAPPIST-1. And this was, we're probably generating a paper a day now on this particular system, okay? Because it's really a very exciting system from any number of perspectives. And of course, if you're really into it, okay, you can start planning your holiday vacation, okay, and do some planet hopping. But after all, it's only a mere 12 parsecs away, and it won't take you too long to get there. So somebody obviously had a lot of fun putting this together. And there were any number of, I mean, what you're going to see, of course, is during the course of this little segment, there are lots of artists' impressions of what goes on. But the exciting bit here, of course, is that you've got 3 planets which are in the habitable zone. In other words, if you have a look at the temperatures that are found at those particular distances from a parent star, there's a possibility of liquid water. Okay, so the TRAPPIST-1 system, let's see, how do I want to do this? Okay, I'll move back and forth here a little bit. Basically, the news release occurred after the Spitzer observations and the Hubble observations, but their observations actually earlier than that. E, F, and G, normal naming convention. I don't think you ever start with A. You always start with B, and you work your way along just in case there's one earlier. To be honest, I don't know. But essentially, E, F, and G are in that habitable zone, and there's a possibility. I mentioned this business of a paper a day, right? Somebody got really excited and say maybe H is in there as well, because the normal way of looking at the habitable zone means you have a certain set of assumptions, but if you have a look a little farther out, maybe you can have some hydrogen outgassing, maybe you warm things up enough that you've got a nice warm blanket, and so you can actually extend the habitable zone a little further out. The star itself is cool, somewhere in the order of about 2,600 Kelvin is a red dwarf, I think provisionally known as an N8 star. It's a red dwarf, and these guys are, they're cool, they're small, they're Jupiter-sized. Okay. Is it a brown dwarf? Well, maybe, maybe not. But it's about 12 parsecs distant in the constellation of Aquarius, and I mentioned that it was 12 parsecs away. Its apparent magnitude is around about 19, and its absolute magnitude is going to be pretty close to that too, right? Okay, well, we won't worry about that. So it's dim, basically, and there's a number of very exciting things about this collection of planets. And if you actually have a look at the orbital periods, then they're basically in resonance. It forms what's called a neo-resonant chain of orbits. So if you actually have a look at the orbital periods, they're simple integer fractions. So that means that they're basically sort of locked together. The other thing that to look at is that they're probably tidally locked to the parent star. So think moon, okay, one side always towards us. All right, that means then that radiation you're getting is nice and warm on one side and not really very warm on the other side. So if you're going here on your vacation trip, make sure you specify a spot along the terminator unless you're really brave. And our meteorologists would probably say, okay, be prepared for high winds. The Hubble observations means that you can actually have a look at the atmosphere, and you basically use the starlight as a probe through the atmosphere, and you check for the presence of hydrogen, usually compounds, and you find that. So they're actually able to tell that we're probably looking at terrestrial type planets. Okay, so how do you build up this sort of this sort of picture? I present sort of the results, straightforward, and we'll come back to the actual observations in a moment. So there we have what people really like as the putative habitable zone. We just push it out to H. The system is, think like a Jupiter system. After all, you've got a Jupiter-sized star and a nice collection of satellites, okay, strung out. But it's larger than the Jovian system. But of course, we can fit all of this stuff inside the orbit of Mercury quite comfortably. Right. So that gives you some sort of perhaps sense of scale. And basically, the sizes are charted there for you. So the issue is perhaps how you actually come to decide on what the actual sizes are. And that's an interesting little problem. I want to backtrack just for a moment and have a look at basically why is it called TRAPPIST-1? It's because there's a project called TRAPPIST. I think astronomers or anybody who has some sort of project name really likes groovy acronyms. All right? So here we've got transiting planets and planetesimal small telescope. And that tells you what the project is really all about. What you want to do is you want to be looking at exoplanets, you want to be looking at planetesimals within our own system, and there's some cometary studies that are actually done by this system of 2 telescopes. They're relatively small. They're 60 centimeters in diameter. One's located in Chile, nice and high, and the other one's in Morocco, and of course, sort of in the desert. So when this particular system of 2 telescopes became operational, this is one of the first, this was the first object that actually the network had discovered, and they noticed that there were 3 objects. Okay, basically transiting the disk. This will come back to what that actually means in a moment. So once you've got a discovery of that sort, then you start to bring the big guns to bear on the object. And so you have a look at it with Spitzer. Spitzer looked at it for 21 days straight. All right, that's a lot of time to do that. And then, of course, Hubble was trained on it as well. And that was basically what the atmospheric is. The acronym is a reference to the famous Trappist order. Think beer, because after all, when the people at the University of Liège in Belgium decided to celebrate, there was no better way to do that than, of course, with a glass of beer. Okay, the actual observations, what you do is you monitor the light coming from the system. And so that nice sort of scattered white band that you see out there are the individual observations. These are now the Spitzer observations. And every once in a while, what you see is a significant dip, okay, in the curve. So you see the sort of the narrow gaps, and you actually see the points a little further down. Don't worry about the broad gaps. Those are actually breaks because of the transmission of the data back to it. Okay, so that's actually, if you like, a loss of data. And what you see then is over that period of time, the various planets were orbits can be determined, so you determine periods, and the amount of dip, just think for a moment, okay, on the side here, we're looking at things crossing the disk. The size of the planetary disk against the sun, okay, is basically you determine the size of the disk. Okay, so you can get this information from fairly readily. Okay, how would you like to participate in something like that? Well, it turns out, in fact, you can join the exoplanet hunt, but using a slightly different technique. It turns out that at Carnegie Science, the Earthbound Planet Search has recently released their data to the public. Okay? And so this is kind of exciting. They're basically, you know, astronomers always had a wealth of data, and sometimes it's just too much for a small group to sort of handle. And one of the things that we find in the professional community is that if you have amateurs, or anybody really, who's interested, okay, in participating in some of these projects, okay, they're welcomed with open arms. And in some instances, it's just because, you know, your eye and your brain pull things together much faster than the computer can. They're much better at that kind of work. But in any event, the data that was recently released is radial velocity observations. So what we're looking at then are basically changes in a particular spectral line, moves back and forth. Okay, we've got the red shift and the blue shift. Okay, so the object is moving towards you or away from you. And essentially, when I've got one object orbiting around another, okay, you see that back and forth motion of, if you like, the parent body. And the equipment is sophisticated enough that you can measure it down to the order of meters per second. Okay, so that's made possible by basically the improvement in the instruments. And of course, when you've got a Keck telescope to use, all right, you got lots of light gathering power as well. So this is done with the 10-meter telescope on Mauna Kea in Hawaii. They have 20 years of data, okay, on something like about 1,600 nearby stars within 100 parsecs. And typically, what they're looking at, because there was a bias, particularly at that time, is to have a look at FGK, and M dwarf stars, basically the remaining sequence stars, stars which are sort of maybe a little bit brighter than the sun, okay, and some which are somewhat fainter. For those of you who want a little more detail, okay, there's something like about 61,000 observations, 30 seconds to 20 minutes duration, and as I mentioned before, precision is anywhere to 3 to 5 meters per second. The cool thing is they have some custom software that we've also released, a tutorial, so for the armchair astronomers amongst you, okay, you can sit down at your computer and play.
From the start, but how many
Yeah.
kilometers roughly is that?
Thank you, Brendan.
I never memorized. As a young kid, I didn't get to experience. I didn't get to experience anything like Voyager. Voyager spacecraft, plants we've never seen that. And obviously, in recent years, we've had some pretty amazing visions. Getting to see Sirius for the first time and Comet Cherry-Love from Kira-Savenko was pretty incredible. But I think I can speak for everyone when we saw the pictures come back to the horizons, we were all blown away. And not just the pictures, but all the subsequent data that came back with it. And it has been truly incredible. So I'm really excited. I'm really excited to introduce our featured speaker tonight. Our speaker tonight is William B. McKinnon. He teaches in the Department of Earth and Planetary Sciences at Washington University in St. Louis. His research focuses on the structure, origin, evolution, tectonics, and bombardment histories of outer planet satellites and icy bodies in Kuiper Belt, as well as fundamentals of impact cratering throughout the solar system. He is a science team member on NASA's New Horizons mission to Pluto and the Kuiper Belt, where he serves as a deputy lead for the geology and geophysics/imaging theme team. He is also a science team member for ESA's upcoming Jupiter Icy Moons Explorer mission and NASA's upcoming Europa mission. So, if you could all join me in welcoming William B. McKinnon.
Great. Well, thank you very much. It's a real pleasure to be here. As I mentioned to a number of people already, I feel really welcomed here in Canada, the land of my birth, and also by the weather, which is very Pluto-like. So I'm going to tell you a story about how we have finally reached the final frontier, at least of the classical solar system. But first I want to send the Wayback Machine back about a century. Okay, and I want to begin this story with this gentleman, who I'm sure is known to many in this audience, Percival Lowell, all right? Son of a very wealthy Boston family, world traveler, Orientalist, but absolutely fascinated with things astronomical. Perhaps something of an eccentric. Okay? He's most famous for popularizing the idea that Mars was inhabited by a dying civilization. But his other passion was to find a new planet. Okay? He wanted to duplicate the feat of Adams and Leverrier, did by predicting successfully, mathematically predicting successfully, the position of what now is the planet Neptune. One of the great things he did with his fortune was found an observatory in the hills above a small town called Flagstaff in Arizona. It's a wonderful observatory, still active today. And it was there he dedicated, he and his staff dedicated themselves to studying both Mars and various oppositions, and of course to search for planet X. But he died without that search being successful. So the baton actually, though, was passed because after he died, the people at Lowell Observatory hired somebody else to carry on the work. There's a young man named Clyde Tombaugh, born in Illinois, not too far from where I live actually, and then moved to Kansas with his family and lived on a farm. He also loved astronomy, but they had no money, And so what Clyde, of course, did was built his own telescope from old farm equipment, and if something couldn't be gotten, maybe he got some, but he could maybe order things from the Sears robot catalog. He sent his diagrams and drawings of Mars and Jupiter to the Lowell Observatory for comment. And they were so enthused with his skill, and of course he was a young man, and it was the Depression, that they simply offered him a job. It didn't pay a lot, but Clyde figured he would never get off the farm. Okay, so he eagerly accepted this offer. He took the train from Kansas City to the west. And here he is, just a little bit later, working at Lowell Observatory, holding a big glass plate that he's exposed at night. And then he develops these himself, and he puts them in his blink comparator, and I think many of you know the story. In not too long a time, searching the star fields that Percival Lowell had predicted a new planet would be found, he did in fact find an object. And that object, these are the discovery plates, that object is this tiny dot at the end of this arrow, which in another plate is over here. This was big news during the Depression, okay, when people were very depressed, right? 9th planet discovered at the edge of the solar system, first in 84 years, lies far beyond Neptune, sighted after 25 years search begun by Percival Lowell. Astronomers hailed the findings. The sphere, right here, possibly larger than Jupiter, meets prediction. Well, okay, we didn't get it all right, but okay, it was still an astonishing, feat. And it was a harbinger of things to come, except it was a long time coming before we really learned very much about Pluto, or indeed that it was part of an entire new realm of the solar system, which we now call the Kuiper Belt. So for a long time, Pluto was simply an outlier, a mysterious body at the very edge of the solar system, which by all rights it shouldn't be there. Maybe it wasn't there. Here's one of these, graphs you might see in a textbook, where there'd be a cluster of orbits close to the sun. The terrestrial worlds, Mars and Venus, and the Earth, of course, and Mercury. And outside then, there's the asteroid belt, and then there's the realm of the giant planets, a kind of second zone. The giants, Jupiter and Saturn, and what we now call the ice giants, Uranus and Neptune. And then there's Pluto, in magenta there. Its orbit isn't in the plane of the rest of them, and you can't quite tell with this figure, but it is in fact an eccentric orbit. In fact, it passes inside the position of the orbit of Neptune during its nearly 250-day circuit, 50-year circuit around the sun. So it was an odd ball, and we learned very little. We couldn't even figure out how big it was. The famous astronomer Kuiper spent a lot of time trying to figure out, just looking at Palomar in the middle of the 20th century. But eventually there were breakthroughs. Many of you, I think, in this audience will remember back in the 1970s when astronomers at the U.S. Naval Observatory actually discovered that, in fact, Pluto had a bump, which turned out to actually be just a blended image of Pluto and its giant, relatively giant moon, which caught people sharing. That was back in 1978. Occultations and transits of the two bodies, which now really we recognize as a binary system, actually showed us what the true size of Pluto is. And of course, because you have the orbital period, the 6.4-day period, and the size of the swimming events to the orbit, you can use Kepler's third law and get the mass of the system. And we knew, in fact, that Pluto was not a big planet like the Earth, certainly not bigger than Jupiter, but in fact was smaller than our own moon. But it has a big moon, so it's a binary world like the Earth and the moon, and there's actually a sort of common thread there that has to do with their origins through a colossal impact, suitably scaled. About 10 years later, we learned that Pluto, of course, was not just some sort of just space lump, but in fact had a kind of planetary character. Not only did it have a big moon, but it had an atmosphere, because we could watch a star go behind Pluto, and we could actually see the light dim and then rise again. And we've done this dozens of times. Really probed this atmosphere. Then by doing this, you can figure out the molecular gas, and bingo, it turns out to be 28. It turns out basically close to nitrogen. It's a nitrogen atmosphere, but no matter what we did from the ground, or even from space, like with Hubble, 10 years later from that, this is the mid-90s. This is the best picture of Pluto. Like, and we've already been to Neptune, been to Triton, it's been all sorts of stuff. So it's still this mysterious, fuzzy place that it's very, very hard to learn anything about. So certainly all of us, a bunch of us in the United States anyway, we really wanted to complete the job because we had grown up and we had seen all the planets and of course the moon revealed to science, and we wanted to science the heck out of Pluto. But the question is science enough? And actually the answer is no, it's not. We really have to put your nose to the grindstone, and you have to develop a kind of advocacy for what you want. Especially, you have to, in the U.S. anyway, we have to convince both NASA, the government agency, and Congress, the source of appropriations, to actually do this. So a bunch of us younger people got together right around a little bit after the time that Voyager passed Neptune, and that was in 1989. Here's an early picture. This is actually the first of a long series of committees that I and others served on to try to advocate for this continued exploration of deep space. This is the Outer Planets Science Working Group, April 1991. It's actually me on the right here. Okay? And this guy, who looks like he's just right out of high school, is Alan Stern, who turns out to be the future principal investigator for the New Horizons mission. All through the 90s, those of us in what we can call ourselves the Pluto Underground advocated. Of course, we were the younger crew at that point, so what we were trying to do was convince the grown-ups. Anyway, it was a long road, and I won't torture you through it all, but there are many proposals, many different kinds of ways to visit Pluto. Some of them were simply technologically premature. Some of them were too expensive by a lot, and some were simply crazy. Okay. So all of these ideas, which are all real, one after another, these were the roads not taken. And only this last one, the New Horizons mission, received the green light, in Hollywood speak, to go forth and explore Pluto in the year 2001. Part of the reason I think this actually occurred was simply the romance of the unknown. Pluto, Mars, and especially thanks to Percival Lowell, has always been this abode of green-eyed Martians and whatnot. But Pluto was just this enigma. So if you go into the literature of Pluto, you find mysterious novels about the secret of the ninth planet. Some of you may read Kim Stanley Robinson's books, like his Mars trilogy. So he wrote a book about Pluto called Ice Age. Okay. And I remember anyway, there was even a Doctor Who episode, right? Tom Baker, Doctor Who, that is. And so he goes to Pluto in the far future, of course, in the TARDIS, where Pluto is no longer cold. Okay. As you can see by their attire, it's much nicer. The sky is overcast, the air is breathable. It's remarkably like England. But of course, this is not what truly sold, I think, the mission, but this is what happened. Is we discovered there were more bodies in deep space. Starting in 1992, astronomers using CCDs, which came over from the military, began to discover new bodies. And you can see as opposition comes around every year, more and more of these new worlds. And then some big worlds like Eris are found, and then Makemake and Haumea. And so hundreds and then thousands of new worlds are discovered. This is the orbit of Neptune, and that's Pluto down there. So this, all of a sudden, we have discovered an entire new zone of the solar system, a torus of many more bodies and much more mass than our asteroid belt. And of course we call this the Kuiper belt now because Carl Kuiper predicted it in the 1950s as a source of comets. As of last month, the Minor Planet Center in U.S. keeps track of the orbits of these things, we have basically over 2,500 identified trans-Neptunian worlds, which includes things that are near Neptune, Trojan, and so on. 4 of these are even classified as dwarf planets, right? Not just Pluto, but Eris and Haumea. Okay. Pluto remains the largest of these bodies, and this is the 3rd zone of the solar system. Terrestrial planets, giant planets, now the Kuiper Belt, the realm of the icy dwarf planets. So we basically got the green light to go, and it's a tale of extreme exploration. It's just as Pluto is an extreme world, exploring it required extreme measures. We got to go ahead in 2001. We rushed to build the spacecraft because we wanted to launch by 2006. In fact, we got off the ground on the 19th of January in 2006 because we wanted to get to Jupiter. We wanted to get to Jupiter a year later so we could take a left turn and scoot across the solar system. Scooting, of course, in this sense means we're taking almost 10 years to do the entire flight. But if Jupiter moved too far out of alignment, well, we wouldn't have that gravity assist, and the journey would have taken another 40 years. And so we really wanted to get, that's what we proposed in that, so that we would get to Pluto in under 10 years. But we had to make that launch window, and we did. July 14th, 2015. Now fading into the past. But we're not actually done. We're actually continuing on through the rest of the Kuiper Belt, and in fact, point of rendezvous with a much smaller body that the Hubble Space Telescope discovered in 2014. And we call it, right now it just has a designation MU69. But that day will happen on New Year's Day, on 2019, so that's less than 2 years away. Let me tell you a little bit about our bird. We're going to get to Pluto in under 10 years. You can't send a giant monster, okay? You have to build the most compact and most advanced spacecraft you can and put it on the most powerful rocket you can buy so you can go fast. So here's the New Horizons spacecraft being built at the Applied Physics Lab between Baltimore and Washington in the state of Maryland. Here's the antenna to communicate with the Earth. Here's some Oompa Loompas. I mean, these are technicians and clean suits. And this black fin demon here is our power source. It's not fuel right there. That would be a bit dangerous. So this is our RTG, radioisotope thermoelectric generator. So far from the sun, we're going to turn the heat of radioactive decay into electricity. So we actually load this thing with plutonium. Okay, so we sent plutonium to Pluto. It's so fun. But you can see it's not that big. You can roll it around. It's, dry mass is maybe on the order of 500 kilograms. It's about the size of a baby grand piano. All of the instruments are bolted into the spacecraft, and so all the different observations have to be done by rotating, turning the spacecraft one way or the other, and we do that with thrusters. So I'll just take you on a very quick tour of some of this instrumentation. Some of this stuff is just designed to study the particles coming from the solar wind. So there's like an instrument called Solar Wind at Pluto, SWAP. And there's a similar particle instrument called EPSI. The antenna is a radiometer to measure heat radiation, but we can broadcast radio waves from the Earth that can sound the atmosphere of Pluto. So we do that as well. And down here at the bottom are stuff that you guys probably will really like. The imaging systems. So we have a CCD, a framing camera, a 1 megapixel, 1 megapixel framing camera, a long range reconnaissance imager. Alice does ultraviolet stuff for us, and then there's a very complicated camera called Ralph, which doesn't stand for anything, it just goes with Alice. And I know it's terrible. It's a scanner, but it can scan in time chromatic, but it also does colors, and there's an infrared spectrograph, so we can actually take infrared images, and it's these infrared spectrometer images that tell us what's on the surface of Pluto at any given position. So this is how we can identify all the strange and exotic ices that live here, which I'll get to. Anyway, I said we want to build a compact spacecraft, and we buy the most powerful rocket we can, built by Atlas V. There's the spacecraft. It's that little tiny thing up here. That's the third stage, that's the second stage, and there's the first stage, and 1, 2, 3, 4, 5 solid rocket motors on the side, all designed to get the machine off the Earth and moving as fast as possible to its destination. So we all showed up in January of 2006, and launch day was there, and then what happened? Nothing. Because it was windy. Okay, well, what do? You know, this is what happens in the launch business. If it's one of the things you can do, if it's too windy to launch and you're in Cape Canaveral, Florida, you should do what I do. You take the kids to Disney World. Now, I get this question. People say, why did you name a planet after a Disney character? I can assure you, this is actually not the way it happened. This young lady, Venetia Burney, okay, in England, was 11 years old when she heard about Percival Lowell's Planetombos discovery, and she wrote a letter, or had her uncle send a letter to Lowell Observatory suggesting the mythological name Pluto to the Lowell people. The Lowell people actually love this idea, and especially because Pluto begins with a P and an L, just coincidentally like Percival Lowell's initials, and also it kind of fits in with the mythological theme of Uranus and Pluto, and so that's where the name comes from. And it's around this time that Walt Disney needed a name for Mickey Mouse's dog. So that was in the news, and so the flow is in the other direction. One of the nice things about all of this is that, of course, Venetia Burney grew up, and in fact, here's Alan Stern later as the PI visiting her in England, giving her basically a certificate of appreciation from the mission. This is before the launch. She actually did not, unfortunately, live to see the actual encounter, but she was on the first week. Anyway, after the Disney World adventure, there was some other monkey business, but then on January 19th, we finally made it. And I have sound for this, but you'll just have to trust me that we actually launched, I'll just shoot.
8, 7, 6, 5, 4, 3, 2. We have a mission to explode liftoff of NASA's New Horizons spacecraft in a decade-long voyage to visit the planet Pluto and beyond.
I never get tired of watching this stuff, you can understand, so I always like to show it. In the interest of time, I will skip ahead. It really it took off from the ground like a bat out of hell, literally. It is the fastest spacecraft ever launched from the surface of the Earth. I like to show this figure. So this is actually the graph. There's the moon's orbit around the Earth. It's a little bit distorted from the projector, but basically our trajectory from the Earth to the moon was a straight line. Right? The Apollo astronauts took a curving ellipse to the moon. It took them 3 days. Of course, they wanted to land, so they didn't want to just shoot past them. So anyway, we got to the, if you want, we crossed the orbit of the moon in 8.5 hours, and we're moving fast enough to, of course, reach the planet Jupiter in 13 months. And then ultimately we reached the Pluto system. And I say it's a system because when we started the mission, Pluto had a big moon. While we were building the spacecraft, the Hubble Space Telescope discovered that there were 2 more small moons along with Sharon. And while we were flying, Hubble spacecraft discovered 2 more small moons, even smaller. So by the time we approached the system, there's a whole family. So Pluto and Charon are kind of like a binary in the center here, and there are 4 small moons, all in a plane, all going around in the same direction. So it's a little miniature planetary system. So it's just one more planet-like configuration for Pluto. Nix and Hydra, Styx, and of course the river, and Kerberos, which is related to Cerberus. So just to make it clear, here we are taking off from the Earth in this graphic. We're going to rendezvous with Jupiter and take pretty much of a hard left when we get there, at least from this perspective. And then we're going to shoot across the solar system, taking years, crossing the orbits of the giant planets. They're not necessarily there to meet them like Saturn's over here, so we don't get to visit anybody else. But we are going to meet Pluto as it's coming down in its elliptical and inclined orbit. And in 2015, we zoom by it at 14 kilometers a second, and then we head off into the Kuiper Belt. So now, the next stage of all of this is what actually happened during that run. So it's time for the encounter in July. And as I say, we were moving really fast. And here's a graphic that shows kind of we're coming, Pluto's orbit, or Pluto's spin axis is tilted over more than 90 degrees. It's kind of like Uranus, okay, to the plane of its orbit. And we were approaching it almost bullseye face on. So we're actually zooming through the system. We're moving really fast. Each one of these takes us 10 minutes. You can see like each one is an hour. These are like the big bar in hours. So we're going to dive through the system here and pass through the shadows of the solar shadows of these moons, so we can actually use the ultraviolet spectrograph, looking back at the sun and see what's up with the atmosphere. All of this has to be done very quickly, as you can imagine, because all the great science, we have a lot of before and after science, but the great science is during these critical hours. It's all choreographed, it's all computer scripted, it's even practiced. We practiced it a whole year before, taking all sorts of non-data in empty space. It all worked amazing. Here's a kind of computer simulation of what those critical hours around the encounter were like. The spacecraft is doing all of these things, it's making all of these scans. You can see up in this box what instruments are being used and how Pluto is appearing in the various views of the various instruments that we're scanning back and forth. We take some time to look at the other moons a little bit, but mostly we pay attention to Pluto and Charon. And now we're just about an hour away from closest approach. We're going to zoom by, looking at them both, taking the highest resolution pictures that we can, and then sweeping past, we can now start to look back at Pluto, passing in front of the Earth and the Sun to do those occultations. And then similarly with Charon. We spin around because we're giddy with excitement. Actually, we're taking measurements of the particle point, taking some very, very long range, and then the system just fades off into the distance. And it was an extraordinarily exciting moment for me and for all of my friends. The morning of the 14th, this was the image that came up on the screen. This was the image that we had taken right before actual closest approach, last full frame in the LORRI camera, because we wanted to have some data on the ground just in case we hit something at 14.3 kilometers a second and destroyed the spacecraft. So all of that, we finally revealed the surface of this mysterious planet. And it was, this was in the room where we were working, and then there were other sort of more public rooms, and there was all sorts of mad celebration of various sorts. But the real treasures really came down the next day, because all of that data had to be taken and put on the solid-state recorders. We had two 64-gigabit solid-state recorders, but we didn't have time to send the data back. It was too important to take the data, and that had to come back later. And of course, the baud rate is not great for that, that's so far away. So in fact, our data downlink lasted for more than a year. We got the very last bits of data from the Horizon spacecraft down just last October. So it was over a year in the summer months. Maybe in the future we'll improve on that some way. So what does Pluto really look like? I showed you a picture of a picture. So this is one of these better pictures. So this is kind of like the natural color version of Pluto on the hemisphere we flew by, the so-called encounter hemisphere. There's a little graphic that shows kind of the view we're looking at. So there's the equator, there's the north pole of Pluto, So the North Pole's up here, the equator is on this dark band, and then there's this bright white thing, which, if you squint, looks like a heart. So we still refer to it as the heart. So you can go online and buy all sorts of great bumper stickers that say stuff like this. I don't get any money from this group. Actually, this is, so we call this Pluto's heart. Actually, the real heart of the encounter was the evening of the 14th. The evening of the 14th was special because that's when most of we couldn't return the data at that time, but we could. It was pre-programmed that the spacecraft would turn to the Earth and radio back some simple commands, just giving it an update on spacecraft health. Like, if it was destroyed, it wouldn't happen. But if it worked, the spacecraft would turn to the Earth. And this is the actual moment, the very moment, when this lady, Alice Bowman, who's the mission operations manager, and NASA EASE, that spells mom, she's getting the word from the Deep Space Net, from the Goldstone tracking antenna in California, that we have symbols. That's what they said, we have symbols. That just means that the first bits of data, that means the spacecraft survived. And then the engineering data came down, and it said that everything seemed to have worked. Like, it said how much the data was on the recorders, like, you know, how much stuff was on your computer, right? It actually had like the amount of data we expected. And the thruster count was right, you know, because it's all pre-programmed. And so it's like you watch Swan Lake and you know how many steps you're going to take. And we basically, all of the steps were taken. We don't know which one, but the number was right. So we knew this was truly fantastic. So then the rest of it has just been like this amazing ride through a world of data. I thought I would just show this because people ask me, like, well, what did you guys actually do? So we had this big room, and we divided ourselves up by themes where people had different kind of interests, as opposed to being focused on your instrument or my instrument or that kind of thing. So down here at the end are people working on composition. So they're using the infrared instrumentation. And then there are people working on particles and plasma. They're interested in that solar-wind interaction. And we have people who are just devoted to the atmosphere as thin as it is on Pluto. And then there's the good stuff, geology and geophysics. And so that's me and our buddies, and we're just having a grand old time. I could go on and on. So let's talk a little bit about what we found. Before I get to Pluto, let me just give a tiny bit about the satellites, right? Because there are 5 satellites. There's a whole lot to actually look at, so I can just give you a little bit of tips. The small satellites are lumpy. Small satellites generally are lumpy. Some of them we saw well, some of them we didn't see so well, but mostly it's because the ones we didn't see so well are the smaller ones. So here's the family of 4. Nix is here, Hydra is here. Each of these scale bars are 10 kilometers, so you can see that the Styx and Kerberos with the same scale bars are much smaller. You can even see the oversampled pixels. So they're kind of space lumps. The cool thing about them is that they're really very reflective, and from the spectra we know, in fact, they're made of water ice. Actually, Nix and Hydra have ammonia ice. And they're also spinning in insane ways. Okay? The little moons, this is actually Pluto and Charon here, they're tidally locked with each other. So they face each other the way the moon faces the Earth. But the other moons are just doing all sorts of crazy things. They're spinning around. Let me go through it again. They're spinning, they're not tidally locked. They're spinning in some ways. This one is rotating backwards. This one is going very, very fast. They're insane and they need to be talked to. Anyway. So it's lots of stuff of interest to dynamicists. What about the big moon in the center, which is one of my favorites? Here's an actual scan, one complete scan, which shows both Pluto and Charon in the same view. It's not a composite, it's not a mosaic. That's what they really look like. These are the faces how they look to each other. Pluto is a little bit, tan or reddish in spectral slope, and Charon is grayer. And it's about half Pluto's size. But when we blow Charon up, it turns into this wild ice moon. Well, it's like a classic ice moon. You've seen pictures of some of the mid-sized moons of Saturn or Uranus. You see stuff like this. It isn't actually stretched out like this. It really is a sphere. The surface of Sharon is made of water ice. It has great canyons and rift valleys that have broken up across. There's a kind of smooth zone towards the south here, which I'll show you a close-up of, and it has a reddish, darker north pole. I want to just show you some of the kind of blow-up of this part. So here's these great canyons that have split. Now these things are like, these cliffs are like 5 kilometers high. Okay? And you can see impact craters, which are sort of classic, dotted everywhere. So we know that the area is not so geologically young. In fact, we estimate that this whole scene here probably, well actually if you look at it, you have some if you look in the telescope, as you guys have, at the moon, this is a very lunar mare-like surface in terms of its crater density, and we think it has a very similar age, almost 4 million years old. Except that this isn't basaltic lava, this is water and ammonia ice. So we actually think the lava here was a kind of viscous mixture of water and ammonia. It's chilled maybe to close to minus 100 degrees centigrade, but still flowing. And we have names we assign to things that are still informal, but we are going to propose these to be IAU in short order. So we actually like to call this one the plain of Vulcan, or Vulcan planet. And the name we assign to the reddish spot on top of the North Pole of Sharon. It really is at the North Pole. Mordor. Macula just means spot in Latin, so this is Mordor Macula. We actually think this redness is a coating. There's methane gas that escapes from the atmosphere of Pluto and flows off into space. We have published a paper recently which has methane molecules sticking to the poles of Sharon, where it's even colder than cold, down to 20 Kelvin, 20 degrees absolute. And then this gets processed by radiation, cosmic radiation, to redder organics. That's our scientific theory. I have my own theory. Let me show you. On to Pluto. Okay, so I showed you a kind of natural picture, color picture, so we can use the color camera, which actually sees into the infrared, and therefore actually kind of an extended human vision. And when we do that, we can actually see the differences between surface compositions. It shows up more distinctly in the infrared. So here's a sort of color version, extended color version of Pluto. The North Pole's up here, it's a bit yellowish. The dark band around the equator is actually reddish, intensely reddish. I think you can see lots of, even from your seats, lots of detail. You can see that there's topography there. There are round things which are impact craters. There are linear things which are rift valleys. There actually are mountain chains and blocks of strong material sticking up from the surface of Pluto, which we recognize to be, we infer mechanically to be water ice, and we have speculative backs it up. And we have the heart itself, which turns out to be two things. The west side of the heart is this vast, flat plain, and the right side of the heart, or the east side of the heart, is a much more rugged and complicated landscape. So it's actually quite different. We have some great names for Pluto as well. We decided, these are what we're going to propose. So the north sort of polar region, there are also small ones. The north polar region, we'd like to name land, Reggio, personal low. We'd like to name the heart, sort of more broadly defined as the brighter region, is Tombaugh Reggio. The flat part, we have been using the name Sputnik Planitia, or the plane of Sputnik, after the first Earth orbiting satellite. Even Planitia Burni gets a rather large crater over here. You might be able to see that. But my favorite name is Cthulhu Reggio, the dark thing, which actually looks to, we call it, in the beginning, we call it the whale. Because it kind of looks like a whale. There's an and, kind of a spout here. Cthulhu, of course, is a giant tentacle monster in the writings of H.P. Lovecraft. So whether the IAU will go for that or not, I don't know. We'll find out. But Pluto is a sort of a random thing. A little bit about Sputnik Planitia turns out to be one of the most interesting things. It really, You can see craters here. So the edge of Cthulhu here is very, very ancient, very heavily cratered. Sputnik Planitia, though, was this vast area. There are mountains all around the edge of it, but the very center of it turns out to be incredibly flat. And in fact, it's a deep basin. Here's a color version of Pluto where the colors correspond to elevation. We measure elevation by taking all these different images and we make a stereo model of Pluto's topography. So this is Cthulhu here. There's some sort of in the image base. But the basin, the Sputnik Basin, is itself an enormous structure that's about 2.5 kilometers deep. Okay. And the way you make giant elliptical basins on planets is through impacts. So we actually think this is a giant, sort of a giant basin similar to some of the great basins like Imbrium on the Moon or Hellas on Mars. Not only is it a great basin, but it's flat, and it's flat because it's filled with soft, relatively soft, and unusual ices. Even though the rugged topography of Pluto must be supported by the most common ice in the solar system, water ice, we can identify spectrally that in fact methane ice, nitrogen ice, and carbon monoxide ice all exist on the surface of Pluto, and well, methane ice is kind of broadly distributed, but the nitrogen ice and the CO ice they're just really tucked into Sputnik Planitia. We actually think the entire Sputnik Basin was created by the impact of a multi-100-kilometer Kuiper Belt object maybe more than 4 billion years ago, but has been filled in with these volatile ices. We can use the imaging spectrograph to really locate, and this is like early work which we published a year ago, but there's like been more and more high-resolution compositional work, and I'll just show you a couple of examples. So here's Pluto over here. This box we blow up here, and that's just the visible image. So this is in the middle of Cthulhu, there's some craters. There's actually a mountain range here, and this mountain range has snow on it, like in the Rockies. But in this picture indicates where the methane spectral absorption signature is seen. So this is actually methane ice condensed onto the peaks of Pluto, which are 1 or 2 kilometers high. The spectrograph tells us where the water ice is as well, because all of these exotic ices bury the water ice, but they don't completely cover all of Pluto. So the blue indicates where we actually have the spectral signature of water ice. And the characteristic areas are, in fact, the rugged mountains that rim Sputnik Planitia. There's some sort of, if you like, water ice hotspots, which we don't understand, over here on the east. And even the dark area of Pluto has very finely distributed water ice crystals. Because it's actually the warmer part of Pluto. I mean, if you can think of anything warm on Pluto at all. Because this bright ice here, this has a temperature of only, it's not even, it's maybe on the order of, right now, 39 degrees Kelvin, 39 degrees Celsius. Okay. Whereas this stuff here is a good 10 or 15 degrees warm. And that is enough to vaporize the exotic ices. Some of these exotic ices, though, where they do exist, they're soft enough to actually flow. And in fact, we think we have evidence that they flow like glaciers. Probably don't need to remind you all of what glaciers are like, okay? Wonderful flowing rivers of ice, like Athabasca Glacier, just in nearby Alberta, right? Between Banff and Jasper. So, on Pluto, of course, water ice doesn't flow. On the Earth, ice that's warm enough will move downhill under its own weight. On Pluto, water ice is too cold to do that, so it's stiff. It's the bedrock of Pluto. But we see evidence to glaciers on Pluto. Here's an image of the eastern part, the edge of Sputnik Planitia. Here's the rugged terrain, and it's color-coded by altitude, so it goes from the base here several kilometers up. And there are flat areas, and there are stuff that's actually flowing down. In fact, let's look at this blow-up of this box. This box is over here. You can see basically the characteristic patterns of glacial flow. And so the softest material of all of Pluto is solid nitrogen, and the physics of solid nitrogen is such that it will in fact move at 40 Kelvin. Okay, it will move downhill. And we can see up at another piece of the edge of to the northeast on Sputnik. We can actually see this is the flat area. There's a scale bar. Unfortunately, I apologize for the American units. Right? It's a massive press release. And you can actually see the flow pattern of this material moving into the rugged landscape of this sort of topographic elevation. You can actually see nitrogen flowing, breaching an old eroded crater rim and beginning to fill it up. So it's coming down off the mountains on one side and flowing up on the landscape on the other. You can also see a curious pattern. It's just labeled polygonal cells here. You see this sort of tracework. It turns out that there's an entire grid across much of Sputnik Phoenicia. This is a geologic map that we published just very recently. So this is, the important thing is that this whole area is broken up into this sort of cellular terrain. It's all very, very flat, but it's very, very interesting when we look at this close-up, because what these individual cells look like are blisters on the surface of a convecting liquid. So this is a close-up. This is the box here over Sputnik Phoenicia. This is what that looks like. So these are the rugged water ice mountains, which we know they stand several kilometers high, and we know they're made of water ice in the spectra. And then this is the cellular terrain of Sputnik. It's all sort of divided up like this. We think it's the manifestation of convective overture. There's enough rock inside Pluto that there's elements. It's just sort of like your typical meteoritic rock has a certain amount of uranium and thorium and even potassium 40, which is radioactive. These things decay and release heat, just like inside the Earth, and this can drive convection, except this convection in the nitrogen makes a manifestly visible pattern. I've never seen anything like this in the solar system. It's kind of like a lava lamp, but with the top off. And this is a numerical model one of my postdocs has created. And even in 2 dimensions, and if you don't like numerical models, I found this on the internet. And you know everything on the internet is right. This is someone's experiment for a completely different reason. This is hot oil with microflakes in it for visibility. And you can it's just basically churning. So it's rising in the center, flowing to the edges, and sending transferring the heat from the top of this pan. So that's what we think is actually going on. We're actually watching the process of what's called solid-state convection in action. We think this happens, inside the Earth and Mars and places like that, but we can't really see it because the surface of our Earth is much colder. Here's another picture of the edge of Sputnik, where the rugged terrain, a little bit north of the colorized picture is shot, color topography picture I was showing before. And again, we can see these. You can see the flow through channels out onto the plane of Sputnik, and there seem to be streams of material carrying the rocks, but they're rather sort of difficult. These are like, it's actually carrying mountains of stuff. Okay, now, it might be methane ice, which actually is very low density, but it could actually be bits and pieces of the terrain itself, of the icy terrain. As it flows in, it kind of wanders around and ends up getting caught at the downdrafts of these convection sources. Here's the edge of those convective blisters. This is a vat of liquid nitrogen, and if you put it in a pressure chamber and evacuate it, it will cause the liquid nitrogen, which everyone wants to play with, it grows and balloons into a break. It'll boil, and as it boils, it takes energy to boil stuff. The latent heat is consumed, and you can actually freeze it. So this is actually a way that you, in your own backyard, can make liquid nitrogen into solid nitrogen. So this is the stuff we think has filled up Sputnik Phoenicia on Pluto. And the great thing about solid nitrogen is that the density of solid nitrogen is 1 gram per cubic centimeter, pretty much exactly, which of course is the density of pure water. And that means if you have a block of ice, like an ice cube or an iceberg for that matter, which will have a density less than that of water, and therefore less than that of solid nitrogen, it will actually float. Even though the nitrogen is solid, it's soft enough on a geologic time scale that you can actually have icebergs of water ice floating in solid nitrogen. So we think those blocks that are being carried out into Sputnik Phoenicia are in fact icebergs. In fact, you could look in many details, and here's a blog of some of the mountains to the south of Sputnik Phoenicia. So these are the big ice mountains here. These are like maybe 3 kilometers high up to the edge here. And there are lots of little bits that are all sort of nearby. I mean, these are almost certainly icebergs that are floating around. But you know, it's buoyancy is scale independent. There's, for all we know, the mountains themselves are icebergs. You don't know that for sure. Let's look at another edge of Sputnik Phoenicia. So we're looking now, here's Pluto's horizon, there's some great rift, there's some rift valleys. This is the edge, there's a polygonal terrain and outline. And there are all these mountain blocks here, all kind of jumbled up, pushed to the edge. It's almost like a log jam. I want to look. Oh, there's one more thing. So here's this. You can sort of see a circular pattern here. This is actually a smaller but still large impact crater, about 250 kilometers across. And this is the one we want to name after Bernie. But I want to look at this little square, this little rectangle down here, because it shows kind of some of the transition stuff. We blow that up. This is what that looks like. These are great blocks of water ice. You can see their tops, they're rotated, tilted, and it really does seem like the crust of Pluto has been broken into pieces and then kind of assembled into a jungle of geological chaos, as though it was actually floating. Maybe it's not floating anymore, but it was floating at one point. Here's a small lake, a small smooth patch, if you like. It's only 40 kilometers long almost. This is also spectrally nitrogenized. And you can see that there's in fact a higher bench around it. So this lake used to be higher. There's been some sort of climate change. And across a lot of Pluto, we see this sort of fingerprint or washboard pattern, which if you were on Mars, you would say these were dunes. Pluto's atmosphere is incredibly thin and cannot form dunes even of water ice-sized sand particles. Now, this and other evidence suggests to us that Pluto's atmosphere has been much thicker in the past, and its climate was much more vigorous than used to go on. Well, it's getting towards the top of the hour, so I'm going to just sort of show you a few more fun slides. There's just so much to do and look at on Pluto. There are, of course, papers you can find online. A lot of great pile of stuff has been released to the public. We can look at the edge. We can look across the plains of Pluto and see the traditional form of impact craters. So we know it's been bombarded over time, but not every part of Pluto has craters. Sputnik Phoenicia doesn't. It's very, very young. It can't be any more geologically young, 10, 20, 30 million years old. Whereas we think some of these cratered parts go back billions. There's an area. Well, we're not even sure what this is, but we've forced ourselves to, we've convinced ourselves that this strange giant mound, which is several kilometers high and has a central depression that's even deeper than the surrounding terrain, is some sort of Plutonian equivalent of a volcano, except this can't be lava like on the Earth. It has to be some sort of strange mixture of ices of a composition we can't quite tell you. So we call it a cold volcano or a cryo. Towards the terminator, towards the edge of the illuminated terrain, we see something looks kind of like snakeskin, except it's hundreds of kilometers long, ridges that are aligned with the sun. We give it a simple name called bladed terrain. There's some patches of nitrogen ice here. But this stuff is mostly methane. So there's been a paper published recently, not by our team, but it's probably fundamentally correct that this is something to do with sublimation of methane ice in sunlight. And without going very deep, once you really get into the nitty-gritty details of the geology of Pluto, you find lots and lots of evidence for past erosional activity, not just the like here's some more of the washboard, sure, or if you like, dunes on Pluto. But there's lots of evidence for deep incision and erosion of the terrain, formation of what we call alpine valleys. Lots of evidence that glaciers have sculpted the terrain of Pluto where we don't see evidence that they're operating anymore. So there must have been different distributions of the nitrogen ice in the past, almost certainly tied to a higher atmospheric pressure. So we'll kind of wrap up with, let's look in. With a little movie, we're going to zoom in, looking down part of our highest resolution strip across Pluto. We'll go to the very edge of the Pluto horizon, and we'll slide down. We'll start to see craters showing up across the snowy plains of Pluto, maybe exposing interior layering. We begin to see some of that washboarding off into the rugged chaos and broken up region of the mountain blocks, which are all jammed together in sort of fragments, and then out into the plains of Sputnik, Phoenicia, which at high resolution have some very fine texture. It's probably a bit of floating water ice. So the real message of all of this is not just, oh, gee whiz, isn't Pluto great, but I think we all flew there wanting to learn about things and expecting to see something really unique and to expand our kind of like conception of what the solar system is like and how geology operates. But just like in the introduction, we were all of us on the team. Alan was up, and I, and everyone else. We were all blown away by what we found, and there's a very simple lesson. But right? Nature's imagination exceeds our own. I never would have imagined that I would see such a spectacular picture as this, looking back as we pass by Pluto with the scanning, and actually seeing the atmosphere itself. Even though it's very, very thin, there's enough methane in this atmosphere that ultraviolet radiation and cosmic rays cause chemical reactions and haze particles form. You're actually seeing haze backlit by the sun, which is actually up above the top of the screen here. So this is a crescent Pluto, all of the rugged topography we see here. This is a very southern tip of Sputnik, Phoenicia. That's right, Mons. That's the actual pile volcano I've been showing. We look close up at some of these departure images in what we call forward scattering. We can see things that maybe we wouldn't have seen otherwise. So this is the horizon of Pluto. This is probably actually a cloud or ground fog. It's illuminated by slanted sunlight. Here's a colorized picture of Pluto where we're actually looking at the mountainous terrain. These are the real mountains at the rim of Sputnik. You can see the mountains marching off like the pyramids of the earth to the horizon and the hazes. And this, of course, is actually, I pulled this off the internet, so it's been colorized. So it's not, we didn't actually get this picture in color. Somebody draped the color from other images. In fact, then they added the sun, which isn't really over there. But I still think it's a cool picture. But this is the real picture. This is the real Pluto. This is what Pluto really looks like when you fly past it and look back towards the sun. There's actually very thin, illuminated crescent Pluto. You can actually see the atmosphere, and this is basically its natural color. It's Rayleigh scattering caused by all those fine haze particles. So a great boon to the atmospheric team on the mission. I was a boy, I actually read the newspaper, not the New York Times, but I did with my hometown paper, July 15th, actually it says the newspaper is July 16th, 1965. Okay, this is the first interplanetary craft to reach any planet. Okay, been to the moon, but we had no robots completed the Soviet Union. But Mariner 4 was the first spacecraft to fly by Mars and actually take the pictures and not find the canals and not find the civilization that First World War I. But 50 years later, to the day, on July 16, 2015, we reached Percival Lowell's planet X. So the question is, sometimes comes up, is Pluto really a planet? Is a dwarf planet really a planet? Well, the truth is, Pluto is a gateway planet. It's the first of the dwarf planets of the Kuiper Belt to be explored. I don't think it will be the last. In fact, it's hard to even know what else is out there. We don't know where the Kuiper Belt really ends, and really what new and amazing worlds there are to discover. So that's the story of our exploration of Pluto. Thank you. No, flying at that speed, we can't figure that out. What we do know is there's no evidence from the particle instruments that there's an internal magnetic field. So we don't think it's big enough to, let's say, a metallic liquid core. What we do think we have evidence for is an internal liquid water ocean, but buried beneath a couple of 100 kilometers of solid ice. And what this comes from is the overall tectonic pattern on Pluto, which is all due to extension or pulling apart of the crust. And an easy way to explain that is freezing or partial freezing of an internal ocean, because when water freezes, it expands, and that will lift up, causing fracture. And there's a more sophisticated and still circumstantial argument that the position of the Sputnik Planitia is almost tidally aligned with Charon, as though there's excess mass there. And one explanation for that excess mass is like a lunar mass concentration, except that instead of dense mantle rock, as in the case of the moon, we actually have water, which of course is. So that's Pluto may in fact be an ocean world the way many of the we have now learned about icy satellites and other sources. Europa, Enceladus, where we have solid evidence that they have liquid water oceans. But the interesting thing about Pluto is that, unlike Europa and Enceladus, those of you who are familiar with it, like these are both moons that are heated through tidal interactions with other moons in their respective systems, Jupiter, Europa, and Saturn, and Enceladus. Pluto is undergoing no tidal heating whatsoever, so it maintains an ocean simply by breathing into the water. Yes, sir.
How long will this your RASC keep on transmitting it? What does it take to bring further down the line now?
Well, that's a lovely, thank you. I'll give you your $20. What are we gonna, what's next? I'll show you this. So this is where we are as of this morning, the 10th of March. There's a graphic, there's the Earth, where it is today. So this is our trajectory through the solar system. You can see a little jog for Jupiter. We passed by Pluto at this point. Pluto's here now, and we're there. We are halfway, basically, to a rendezvous with this small Kuiper Belt object, which we discovered. Well, we had a big effort with the Hubble Space Telescope to find anything that we could rendezvous with the cluster field we have. So it doesn't have an official, it just has a designation now. It's called 2014 MU69. I believe we're going to have, NASA will try to run a public naming contest later this year to give a real name to this, so you all might be able to suggest something good. But that's what we're going to be doing. We're going to get there in, we'll be approaching it at New Year's Day 2019. It's not a big object. It's only a few tens of kilometers across, but it's an ancient object. It's part of what we call the cold classical part component of the Kuiper Belt. We think it accreted there and has remained there. So we may actually see the true signature of the accretion of bodies in the solar system. Pluto itself isn't evolved. It's not that primitive. And in fact, probably formed much closer to the sun than it is now. So that's what to look forward to in 2019. At the signpost up ahead on the Trans-Canada, it's just about 5 astronomical units. Beyond that, the spacecraft will still work. There's no known target that we can go to. But the plutonium, as it slowly decays and as the thermocouples age, really more important as the power goes down. But we estimate that we'll be able to listen and transmit to the spacecraft reliably into the 2030s. And its utility then to science will be not as an explorer of the Kuiper Belt per se, but to explore the heliosphere, like the Voyagers, or still the Voyagers from 1970s, 80s, are still doing today. So that's for NASA to determine in the future, but we may still be receiving data from New Horizons for the next 15 or more years. Yes, Doctor.
Why didn't they make the New Horizons spacecraft be able to loop around?
Ah, well, we would have loved to do that, but in order to slow down from 14 kilometers a second to much, on the order of 1 or 2 kilometers a second to go into orbit, would have required a huge amount of rocket fuel. And you couldn't launch all that mass with the rockets we had, so we had a choice. We didn't have a choice. We wanted to go there, so this is really our only choice. So that's a tougher plan. It's a tough thing to do. I'm not saying it's impossible. We're actually beginning to think now about how we could go back and what we would like to do. We wouldn't just want to go back and test what we had decided. We would, in fact, want to go to work. And the best idea we've come up with is to couple an RTG, nuclear electricity, with an ion drive, such as the Dawn spacecraft is using in the series. We would not only use a chemical rocket, but we would then accelerate with an ion drive on the way out, and then decelerate, kind of like scenarios you sometimes read about traveling to the stars. With that, and maybe a small amount of chemical rocket braking, we would be able to run it. So I predict that this will happen. Somebody will do this in this coming century. Maybe you.
Would you like to see Pluto restored to planetary status?
You're asking me?
Yeah.
Oh, wow.
How long do we have?
There's a long story here. This is the way I look at it, right? Pluto is small, but it has all sorts of planetary characteristics. So the official IAU definition is it's a dwarf planet. And I'm actually happy with that. It kind of says what it is, it's small. The only sticking point, from my point of view, is the IAU, of which I'm a member, but they don't listen to me, is that dwarf planets are not planets. For dwarf trees are trees. So I think it's in the end a sterile argument, and Pluto doesn't give 2 whiffs what we think. Yes.
One way it wasn't sterile is in getting funding for this. So you were kind of fortunate that this debate took place far enough down the line that you were already committed to going to the planet before it didn't become a planet?
You have a point. It's hard to know what counterfactual history. We were able to launch in early 2006, and that ignominious vote at the Prague AU meeting was that summer. So we were already in flight and they couldn't call us. But you could imagine that if this could have affected, somebody at NASA headquarters in Congress, if that would happen. I'm glad it did. I think that we're all lucky, frankly. It's really beyond all our expectations. Oh, another question.
Yeah.
Oh, okay. And then
I'm fascinated with spacecraft radio.
okay.
What's your broadcast power from Pluto?
The actual transmitted power, I can't tell you that number off the top of my head.
It's not very many watts.
No, it's not very many watts.
So it is like looking at a 10-watt light bulb.
It's something like that. The total power generated by the spacecraft itself is only a little over 200 watts. So everything has to run. You have to keep the spacecraft warm. Excuse me.
It's the radio custom built.
Well, yeah, all these radios are built, for deep space communications. The NASA maintains this deep space command. 3 positions around the Earth, roughly 120 degrees apart. Oakland, California, Madrid, Spain, Canberra, Australia. These are 70-meter dishes, and sometimes they're arrayed with several 34-meter dishes that are just nearby, and they just try to soak up every radio photon. It works amazingly well. But still, our bit rate from Pluto was really only about 1,000, sometimes 2,000 bits a second. When we had DSM come out, things came back right. Yes, sir.
What was the most amazing thing that you found so far?
All of this. That's the most amazing. I'm not sure I can pick. I think I'm personally most thrilled with Sputnik Phoenicia's convection system because it's something that can work on. We have a numerical theoretical tool to really extract information about Pluto. But I think for a lot of people, maybe the most astonishing thing was this evidence for past evidence of a thicker atmosphere, glacial activity. In fact, the theories that we have now for all tie this to the way Pluto's climate cycle is very, very much in the way Mars works. Mars' tilt rocks back and forth. Pluto's spin pole, whether it's pointing at the sun at perihelion, but it's much warmer, or perpendicular, changeable. We think that not only was Pluto much more active in the past, but it will be more active in the future, although in this case, but if we wait. And also, of course, it's kind of like on a meta level, it's like Pluto itself turned out to be really, really interesting. And it stands to reason that the other big worlds out there, like Eris, are probably at least as fascinating, and perhaps as unusual. So I hope that some people get to see these other worlds. Okay, yes?
I just wanted to ask you, it was mentioned that you were part of some other teams as well, for other air spacecraft. And is there anything we can look forward to with some of the other spacecraft that are still traveling?
Well, I mean, I think right now, everybody here, if you want to interested, I mean, there's spacecraft operating, the Japanese are operating Venus, we're orbiting the moon, there's too many spacecraft you can count, busy on Mars. Juno is orbiting Jupiter right now, returning fantastic images. And Cassini, of course, you've seen those mind-blowing images of Pan, the Yankee Gap recently, and of course it's going to shift its orbit, so it's Periaps is inside the D ring of Saturn, and it's going to shift back to the ultimately dive into the atmosphere of Saturn in October. So it's going to be fantastic imagery from the operating spacecraft. And the missions that you are referring to are that I'm involved with right now. We're building a new generation of spacecraft, we mean the human race, to fly back to Jupiter to explore the moon. NASA has in fact advanced a mission to what's called Phase B, given it an official name called the Europa Clipper. Our job is to go back to Jupiter, orbit Jupiter, and encounter Europa repeatedly to explore its habitability with all sorts of instrumentation. I'm involved with the radar team to look through the ice shell to find the ocean, and also to sniff the vapors that are coming off of Europa, looking for honestly signs of life. And there's a companion mission in a way. The European Space Agency is going to launch the Jupiter Ice-Helium Explorer to be the first satellite orbiter that will ultimately orbit the solar system's biggest moon, Ganymede, and I'm involved with that. Both of these missions will play out in the 2020s into the 2030s, depending on what launchers they use. The European mission will get to Jupiter in 2030. The NASA mission might get to Jupiter as early as 2026 if it's launched on the biggest rocket that NASA has ever developed. We don't really know whether the Space Launch System, as it's called, will really work or get the full funding because the situation with the American government right now is bizarre. It's like Yogi Berra once said, another famous Hinduism. It's really hard. The future is really hard to predict. So anyway. Okay. Okay.
Yeah.
All right, well, thank you.
Yeah, I want to say.
Okay.
Thank you.
Okay.
That was incredible.
All right, well, thank you.
A small piece of the solar system.
Oh, excellent. I can always use another meteor.
Okay.
All right, thank you very much.
Thank you. So yeah, for those that don't know, we have a tradition of heading to Boston Pizza after the meeting for pizza and other things like beer. So this is held at the one on Pembina, just south of the university. Also, there is more copy of Sky News. I forgot to mention this, but we just made these out. If you do want a copy of the recent Sky News, come on by and pick it up. Other than that, thank you very much for coming out.